Hello, and welcome to the Sleepy Professor. This is your little corner of the world, a quiet refuge where you can let the day's noise drift away, and if sleep finds you along the way, let it carry you gently while the world continues its slow, steady spin. Tonight, our journey is about something that touches us all, something ordinary, yet quietly extraordinary, the soft, almost secret chemistry of rain. The raindrops that tap softly against rooftops, that trace lazy patterns down windows and seep quietly into the soil. They are not just water, they are tiny dancers of chemistry, moving unseen, shaping the air, the earth, and even life itself. Before we begin, I wonder, where are you listening from tonight? Perhaps tucked under a thick, cozy blanket, or maybe far across the world, eyes tracing the streaks of rain as they slide down your own window pane. Wherever you are, settle in, breathe. Let the rhythms of this gentle voice be a lullaby for your curiosity. If you enjoy these calm, wandering explorations, a like and a subscribe would help this sleepy little channel keep turning, spinning just as gently as the droplets we are about to follow. And for those of you who have already joined this quiet little community, thank you. Thank you for letting this soft, slow corner of the internet exist. Don't worry, I'll try not to make it so fascinating that you stay awake all night. Though if the story of rain does capture your mind a little longer, at least you will drift off carrying a curious whisper of science with you. So, let's begin. Have you ever paused to wonder why rain isn't just plain water? Why it sometimes carries scents, faint colours, even secret ingredients lifted from the sky and the soil. Ingredients we rarely notice, but that change everything, subtly, quietly. Rain is one of those miracles we pass by without thinking. It falls endlessly, nourishing fields, washing city streets. Yet within its simplicity lies a world of invisible activity, of molecules in motion, of chemical conversations that have been going on since long before humans learned to watch the clouds. Rain is more than just water tumbling from above. Each droplet carries hidden passengers, tiny bits of dust, grains of salt, dissolved gases, microscopic traces of life, all clinging quietly, invisibly, suspended in the fall. Rain is chemistry in motion, a story written softly in liquid, a story that shapes the world as it touches it. Some drops leave behind the sweet, earthy scent we call petrichor. Some carve stone over centuries, nourish crops, cleanse the air. Its touch is gentle, but its influence is immense. In tonight's journey, we will drift from the minuscule, the invisible bonds that hold water molecules together, to the vast planetary cycles that carry raindrops across oceans and continents. We will listen carefully to the quiet lessons of storms, trace the minerals and gases hidden in each drop, and reflect on how rain has shaped not only the natural world, but also human imagination and history. As you sink a little deeper into your blanket, into your chair, into this moment of rest, remember that every rainfall is a conversation between sky and earth, chemistry spoken softly with liquid words. And now, with gentle curiosity, let us step into the first chapter, the story of how a single drop of rain begins, its long journey from the sky to your world. High above us, in skies that often seem empty, vast and still, invisible transformations are always taking place. Water that we recognize in rivers, lakes, and oceans is quietly slipping away into the air, evaporating, becoming vapor. Perhaps you've noticed it in a shrinking puddle on a warm afternoon, or a wet shirt drying slowly on the line. This is evaporation on a familiar scale. On a global scale, it is immense. Every river, every lake, every ocean, releasing molecules of water into the atmosphere, drop by drop, molecule by molecule, like a vast invisible exhalation of the earth itself. This process relies on a property of water that is both ordinary and remarkable. Molecules at the surface are always in motion, jostling, spinning, nudging each other. Some gain just enough energy to break free from their liquid neighbors to escape upward into the air as vapor. Temperature is the quiet conductor here. The warmer the water, the faster the molecules move, the more eager they become to float into the sky. This is why the tropical oceans exhale moisture so eagerly, why the sea steams on hot afternoons, and why evaporation never truly rests. Even in cooler climates, the process continues, more slowly, more subtly, but always present. But vapor alone does not make rain. Water molecules drift invisibly through the air, independent, lonely, traveling great distances without ever gathering together. For condensation to occur, for droplets to form, water needs a place to cling, a tiny seed around which it can gather. This is the magic of nucleation, one of the secret steps in the birth of rain. The atmosphere is never empty. Dust lifted by the wind, sea salt flung by waves, ash from faraway volcanoes, soot from chimneys, even grains of pollen floating lazily from forests. These tiny particles become the scaffolds, the cloud condensation nuclei, around which water begins to gather. When vapor meets them, it clings, molecules drawn together by invisible forces, forming clusters, tiny beads, and slowly droplets in the making. Without these impurities, rain would struggle to exist. Even the cleanest air resists condensation. Nature provides what is needed, an almost imperceptible nudge. Yet forming a droplet is a delicate process dependent on a careful, almost whispering balance of temperature and pressure. High in the atmosphere, where the air is cooler, condensation is a little easier. Warm, moist air rises slowly, expanding as it climbs, allowing clouds to gather, droplets to cling. Pressure plays its subtle part too. Too much pressure, and the water molecules collide and scatter. Too little, and condensation falters. But just right, and the liquid emerges, each droplet a tiny alchemist, quietly transforming the invisible into something tangible, a gentle miracle repeated millions of times across the vast sky. Imagine each droplet as a soft dancer, a quiet artist working in the clouds. Water, light and fleeting, is coaxed into form around nearly imperceptible grains of dust. It spins an invisible skin, capturing the essence of sky, air and earth, weaving the beginnings of a cloud that will one day release its bounty. A cloud is not, as it sometimes appears from below, a simple puff of cotton. It is a vast suspension, a floating city of droplets, each carrying quiet secrets from above, impossibly small, often less than the width of a human hair. They hang there, suspended, balanced delicately, between gravity pulling them downward and rising air pushing them upward. Within this suspension, droplets jostle gently, sometimes merging, sometimes evaporating back into vapor, only to condense once more. It is a restless, shifting community, always in subtle motion, a soft, ceaseless dance. This first transformation, from vapor to liquid, is the opening act of rain's quiet chemistry. It links oceans to skies, setting the stage for everything that comes after. Even before a single drop touches the earth, countless interactions have already taken place. Molecules escaping warmth, finding particles, clustering together, obeying the delicate rules of temperature and pressure. To stand beneath a cloud is to be in the presence of this invisible labor. What appears as a soft grey ceiling is in truth billions of droplets, each a tiny, improbable success in the act of condensation. It is almost poetic to think that something as mundane as a speck of dust, a fleck of salt, or a wandering grain of pollen can become the midwife to rain. Without them, the air could hold endless vapor, and the sky would remain empty, silent. But with them, water finds an anchor, and transformation begins. The chemistry is quiet, almost secretive, yet the results are familiar to all. From the puddle on the sidewalk to the thunderstorm rolling over the horizon, it all starts in this silent exchange where vapor relinquishes freedom and becomes liquid once more. If you were to ask a child to draw a raindrop, chances are you would see a teardrop, pointed at the top, round at the bottom. It is a shape so familiar it appears in cartoons, logos, weather icons, even road signs. Yet nature has its own geometry, dictated not by crayons but by physics and chemistry, and the reality is far more captivating. When water hangs in the air as a droplet, one of the forces shaping it is surface tension. Imagine water molecules as friends. Holding hands, each molecule clings tightly to its neighbors through hydrogen bonds, a delicate attraction between the slightly positive side of one molecule and the slightly negative side of another. At the surface, where there are fewer neighbors, the molecules pull inward, creating a gentle, invisible skin. Left entirely alone, surface tension shapes a droplet into a perfect sphere. This is why tiny droplets, like mist or morning dew, are beautifully round. In these small sizes, cohesion is stronger than both gravity and the resistance of air. Mist drifting lazily through the air is a cloud of miniature spheres, each no wider than a single strand of hair, floating effortlessly. But droplets grow. Within clouds, they collide and merge. Once they reach a certain size, the balance begins to shift. Gravity tugs more firmly. Air pushes against them as they fall. Picture holding your hand out the window of a slowly moving car. The air presses softly against your palm. A raindrop experiences the same, only its delicate form can be flattened by this invisible force. Medium-sized raindrops, about 2 millimeters across, no longer remain perfect spheres. They resemble tiny hamburger buns, rounded on top, flatter below. Grow them larger, and the shapes become stranger still. At around 4 millimeters, the bottom can indent, forming something like a miniature parachute. Beyond that size, drops may even split mid-air as the forces pulling them down overcome surface tension. The classic teardrop is a charming myth. Nature's droplets are never neat, never pointy. They are spherical when small, bun-shaped when medium, collapsing when large, each telling a quiet story of physics and chemistry working together. Hydrogen bonding deserves a soft nod here. These bonds last only fleeting moments before breaking and reforming, yet together they give water the cohesion needed to shape raindrops. Without these invisible bonds, water would behave very differently, perhaps not even liquid at temperatures we are familiar with. The form of a raindrop is in many ways the architecture of water itself. And then there is mist, those suspended droplets so tiny that gravity barely even touches them. They float, drifting lazily for hours. Gentle, ghostly, a soft silken veil. Walk through mist, and you do not so much feel rain as a subtle, almost imperceptible embrace. Tiny spheres kissing your skin, held together by invisible threads of surface tension. Cloud droplets are even smaller still, mere micrometers across. Imagine lining up over 100 of these droplets across the width of a single human hair, and yet they float effortlessly, riding gentle updrafts, swaying in the turbulence of the air. Only when these tiny droplets gather into larger clusters does gravity finally take hold, coaxing raindrops to begin their slow, inevitable descent. It is almost humorous how consistently we have misrepresented raindrops in art and cartoons. Elegant, pointy teardrops, blue icons on weather forecasts, even warning signs for slippery roads display the same fictional shape. In reality, a medium raindrop is closer in form to a squashed little hamburger bun than a graceful teardrop. Not as sleek, not as marketable perhaps, but far closer to the truth. Understanding the architecture of a raindrop is more than a curiosity. It affects how light bends and scatters within each drop, creating the rainbows that arch across our skies. It influences how fast the drop falls, how much water reaches the ground, and even how soils absorb moisture. A perfect sphere would behave differently than a flattened oval. Tiny shifts in shape change the way rain interacts with the world, even shaping the sound it makes when it strikes leaves, rooftops, or puddles. Small spherical drops create a soft, delicate patter. Medium drops a more resonant rhythm. Larger drops a heavier, drumming cadence. Every rainfall is a symphony, orchestrated by surface tension, hydrogen bonds, and gravity, performed in perfect silence. Each drop is a masterpiece of chemistry and physics, designed not by an artist, but by the quiet, unyielding laws of nature. There are few experiences more instantly recognizable than the smell of rain. Step outside after a summer shower, or inhale deeply as the first drops strike parched ground, and the air changes in a way that feels almost magical. Fresh, earthy, comforting. A scent that has inspired poets, perfumers, and curious scientists alike. That fragrance has a name: petrichor. Behind its gentle, soothing allure lies a complex blend of chemistry, a perfume crafted by nature itself. The term petrichor was first coined in the 1960s by two Australian researchers, Isabel Baer and Richard Thomas. They sought to describe the distinctive smell that accompanies rain on dry soil. The word is poetic, derived from Greek roots, petra, meaning stone, and ichor, the mythical fluid said to flow in the veins of gods. A name elegant, perhaps lofty, for a phenomenon grounded firmly in the earth. Petrichor begins with plants. During long dry spells, many plants exude oils that seep into the soil, cling to rocks, and linger in the dust. These oils have practical purposes. Some regulate seed growth, others deter competing vegetation. Left to accumulate, they wait, dormant, for the right trigger. When rain finally arrives, the impact of droplets releases these oils into the air, carrying their delicate aroma upward in tiny bursts. Subtle, yet instantly recognizable. But petrichor is only one part of the story. Another key player is geosmin, a compound whose very name means earth smell. Geosmin is produced by soil-dwelling microbes known as actinobacteria. These microbes are ancient, abundant, and tireless recyclers of organic matter. As they live and die, they release geosmin into the soil. When rain disturbs the ground, it lifts geosmin into the air, where human noses, remarkably sensitive, can detect it even in the tiniest concentrations. To put it in perspective, we can perceive geosmin at levels as low as a few parts per trillion, like noticing a single drop of dye in an Olympic-sized swimming pool. Geosmin gives rain its earthy, musty note, the smell of freshly turned soil, the comforting aroma of a garden after watering. Then, there is the sharp, almost metallic note that sometimes accompanies thunderstorms. This comes from ozone, a molecule made of 3 oxygen atoms. Normally, oxygen prefers to exist in pairs, but when lightning splits these molecules, some recombine in trios, forming ozone. It is unstable, fleeting, yet storms can draw it down from higher altitudes, giving the air that faint, crisp tang just before or during a storm. A smell of energy, of renewal, of a world being washed and awakened. Together, petrichor, geosmin, and ozone create rain's unique aroma. No two showers smell exactly the same. A gentle drizzle after a long dry spell may release more petrichor. A thunderstorm may highlight ozone. A forest shower smells different from rain in a city because the soils, the microbes, the plants, all vary, and yet in each case, the chemistry works subtly, profoundly on our senses. Why do humans find these scents so calming? Partly biology. Our noses are extraordinarily sensitive to geosmin, perhaps an echo of ancestral survival instincts, helping humans recognize damp soil as a sign of fresh water. Partly psychology. Rainfall brings cooler air, softer light, rhythmic sound combined with fragrance. These cues evoke memories, associations, comfort. Many people link the smell of rain with safety, with childhood summers, with quiet moments of shelter. Interestingly, not everyone experiences the sense of rain in quite the same way. In perfumery, geosmin, the compound responsible for that earthy, soil-like aroma, can be divisive. Some adore its grounded charm, while others find it overpowering. Yet the natural blend created by rainfall seems to strike just the right balance. Fleeting, ephemeral, it is there one moment, gone the next, a reminder of the temporary beauty hidden in ordinary events. There is even a quiet humor in its universality. People may argue endlessly over food, music, politics, yet set a rainstorm across a dry landscape, and nearly every nose perks up in unison. When you take in that first deep breath after a storm, you are inhaling the combined work of plants, microbes, and lightning, chemistry broadcast into the air, tuned carefully to human senses. Every whiff tells a story. Waiting plant oils released by raindrops, industrious bacteria stirring in the soil, the crackling energy of lightning, stitched together into a perfume that has followed our species for as long as humans have walked the earth. The smell of rain is, in many ways, a reminder that chemistry is not confined to laboratories or textbooks. It is everywhere, quietly shaping experiences we take for granted. Whether it comes as the whisper of petrichor or after a dry season, the grounding wave of geosmin from the soil, or the sharp flash of ozone during a storm, the fragrance of rain is one of nature's most elegant signatures, a symphony of molecules that makes the world feel refreshed, renewed, alive. When most people think of rain, they imagine it as pure water falling from the sky, a distilled gift from the clouds. In reality, every raindrop carries chemistry within it, shaping its very character. One key trait is acidity, measured along that familiar pH scale. While water is often thought of as neutral, with a pH of 7, natural rain is slightly acidic, hovering around 5.6. There is a gentle reason for this. The atmosphere is rich with carbon dioxide. As water vapor condenses into droplets, it absorbs small amounts of this gas, forming carbonic acid, the same weak acid that gives sparkling water its gentle fizz. Though subtle, this effect nudges rain slightly below neutral on the pH scale. This mild acidity is natural and has been a feature of rainfall for as long as Earth has had both an atmosphere and water. This gentle acidity is far from harmful. It aids weathering of rocks, releases minerals into soils, and sustains essential natural cycles, but the balance shifts when other gases enter the air, especially those from industrial activity. Power plants and vehicles release sulfur dioxide and nitrogen oxides. When these gases meet water droplets, they form stronger acids, sulfuric acid and nitric acid, producing rain with pH levels closer to 4, sometimes even 3. This is what we call acid rain. Acid rain became a major environmental concern in the 20th century, though its roots stretch further back. During the Industrial Revolution, coal was the dominant fuel. Burning it released vast amounts of sulfur dioxide into the air. In cities like London and Manchester, this gas mixed with rain to form thick, corrosive precipitation. Buildings blackened, forests withered, rivers could no longer support fish, even marble statues suffered, as acid ate away delicate carvings. Nature itself bore the mark of human industry. Forests were not spared. Acid rain leached calcium and magnesium from soils, depriving trees of essential nutrients, while releasing toxic aluminum ions. Entire stands of spruce and fir withered under this dual assault. In lakes, rising acidity caused fish populations to collapse, eggs and fry unable to survive in the water's chemical shift. The consequences were profound, visible, impossible to ignore. Recognition of acid rain's destructive power sparked investigation. In mid-20th century Scandinavia, scientists observed dying lakes far from industrial centres, tracing the problem to pollutants carried hundreds of kilometres on the wind. Pollution in one place could acidify rainfall far away. Suddenly, acid rain was no longer a local problem. It was a regional, even international issue. Policies began to shift. Stricter emissions controls, scrubbers in power plants, cleaner fuels, catalytic converters. Gradually, the rain became less acidic. Lakes began to recover. Forests showed hints of renewal. Science had made a difference. Yet, not all rain is acidic. In regions rich with dust or limestone, rainfall can be slightly alkaline. Winds lift fine particles of calcium carbonate and other minerals into the air. When rain forms around these particles, it dissolves them, raising the pH, creating rain that is more neutral, sometimes mildly basic. This alkaline rain offsets natural acidity and may even enrich soils. The chemistry of rain, then, is never uniform. It depends on atmospheric gases, dust, minerals, local geography. A storm over an industrial city in the 19th century produced rain very different from a desert storm today. Even within a single system, raindrops carry the chemical fingerprints of their journey. There is irony in this. Rain, so often associated with purity, is in truth a mirror of the air it falls through, a reflection of the cloud's travels over forests, oceans, cities, deserts. Its acidity or alkalinity records the recent history of the atmosphere. For most of human history, rain was simply water from the sky, nourishing, sometimes destructive, often overlooked. Only centuries of observation and modern chemistry revealed that every raindrop is a little laboratory in motion, its pH dynamic, shaped by gases, particles, and human activity. Even a thunderstorm, one of nature's grandest spectacles, is an active laboratory. Clouds tower, lightning cracks the sky, rain pours, but hidden in this drama is vital chemistry. Thunderstorms forge new compounds that fall with the rain, including nitrates, essential nutrients for life. Imagine the energy of a lightning bolt. A single flash reaches temperatures hotter than the surface of the sun, around 30,000 degrees Celsius. At that heat, nitrogen and oxygen molecules are ripped apart, split into reactive fragments. Almost immediately they recombine, some forming nitrogen oxides. These dissolve into raindrops, reacting further to create nitrates, forms of nitrogen that plants can actually use. Though the air around us is mostly nitrogen, it is locked in unreactive N2 molecules. Plants cannot use it directly. They need it fixed into compounds like ammonium or nitrate. Lightning provides one of nature's original nitrogen fixing systems, delivering essential nutrients back to the soil. Long before humans learned to manufacture fertilizer in factories, this was how storms quietly sustained ecosystems. The very proteins in our bodies, the chlorophyll in leaves, owe part of their existence to nitrates delivered by thunderstorms. Alongside nitrates, thunderstorms generate bursts of ozone. Lightning splits oxygen molecules, some recombining as O3, the triatomic ozone we know. Most ozone resides high in the stratosphere, shielding life from ultraviolet rays, but storms create small amounts closer to the ground. A faint, crisp tang in the air announces their presence, a sharp, fresh scent people often describe as metallic or electric. It is fleeting, ephemeral, because ozone is unstable and breaks down quickly. Yet, for a brief moment, it adds to the unique perfume of a thunderstorm, mingling with petrichor, geosmin, and the rain itself. These temporary surges of ozone and nitrates demonstrate the energy contained within storms. They do more than rearrange the weather. They actively alter the chemistry of the sky, performing reactions that cannot be replicated at such scale in laboratories. For scientists, thunderstorms are natural laboratories of extreme conditions. They offer insight not only into Earth's atmospheric chemistry, but also into how similar processes might occur on other planets, on distant worlds with lightning-rich atmospheres. Massive storms on Jupiter and Saturn, for instance, may be performing comparable atmospheric chemistry, only on a scale far beyond anything seen on Earth. Humans, of course, have long sensed the fertility of storms, even without understanding the chemistry behind them. Farmers observed that crops often looked greener and more vigorous after a series of thunderstorms. Rain did more than water the fields. It delivered something invisible but vital. Centuries later, science revealed that nitrates were the hidden gift, the quiet sustenance embedded in every drop. Ancient myths sometimes described thunder as the voice of gods, hurling power and fertility down to the soil. While poetic, these stories were rooted in careful observation of real, tangible effects. Even today, though industrial fertilizers dominate modern agriculture, thunderstorms continue to quietly contribute to soil health. It is estimated that lightning fixes around 5 to 20 million tons of nitrogen into usable compounds each year. Small compared to human production perhaps, but far from trivial. Natural ecosystems, forests and grasslands, still receive this periodic, invisible boost, independent of human intervention. The idea of rain as a delivery system is worth lingering on. Each droplet that falls from a storm carries dissolved gases, nutrients, and a small parcel of chemical history. When these droplets sink into the soil, nitrates spread through root zones, where plants absorb them to build proteins, enzymes, and DNA. From there, the nitrogen enters food chains, cycling into animals, and ultimately returning to the atmosphere as organic matter decomposes. Thunderstorms are not just spectacles of light and sound, they are vital participants in the grand nitrogen cycle. There is a gentle paradox to this process. Thunderstorms often feel chaotic, even destructive. Roaring winds, crashing sounds, and blinding flashes of light evoke awe and sometimes fear. Yet out of that seeming violence comes nourishment. The same lightning strike that startles us also forges molecules that sustain life. Creation and destruction arrive together, entwined in the same bolt, reminding us that nature rarely separates chaos from order. The next time the sky rumbles and rain pours down, it is worth remembering that more is happening than what meets the eye. Inside every storm, atoms are torn apart and recombined. Raindrops become enriched with nutrients, and the soil below quietly prepares for growth, long before a single leaf unfurls. A thunderstorm, with all its power, is in its own way one of the planet's oldest gardeners, sprinkling the earth with ingredients essential to life. Rain has many roles, and one of the most overlooked is its work as a cleanser. When clouds finally release their contents, droplets do more than nourish the ground. Each drop is a tiny janitor of the skies, sweeping up dust, soot, pollen, and even traces of invisible pollution. The effect is a natural house cleaning on a planetary scale, leaving the world refreshed, clear, and slightly sparkling. This process begins even before the raindrop leaves the cloud. As water vapor condenses around particles, it traps what is already suspended in the air. Tiny bits of sea salt, smoke, volcanic ash, industrial emissions, even microscopic fragments of organic matter. Scientists call this process scavenging or rainout, the capture of particles during droplet formation. In essence, the drop is born already laden with the atmosphere's clutter. As raindrops fall, the real magic continues. They collide with and absorb other particles drifting in the air. Scientists call this washout. Imagine billions of tiny vacuum cleaners falling silently through the sky. Each droplet sweeps up whatever it encounters, dust floating high above, smoke from chimneys, pollen grains, even microscopic debris that irritates our noses. Rain literally scrubs the air, not with machines but through chemistry and gravity working in quiet harmony. The difference is easy to notice. After a heavy shower, horizons look sharper, colors more vivid, the air feels lighter. This freshness is no illusion. With fewer particles scattering light, visibility improves. Fewer airborne pollutants mean less irritation to lungs and sinuses, which partly explains why stepping outside after rain can feel invigorating, even restorative. In cities, the effect is amplified. Urban air carries particles from traffic, construction and industry, soot from engines, microscopic bits of tire rubber, dust from endless building projects. Rain offers a temporary reset, lowering pollution levels and clearing the view. While the water that reaches the ground may carry these pollutants, the air itself feels purified for a time. In rural areas, the cleansing is gentler, but equally profound. Pollen, spores, dust stirred by winds, rain presses these back into the soil, giving the natural world a reprieve. Farmers have long welcomed rainfall not just for hydration but for this subtle air-clearing effect. Forests, too, benefit. Leaves washed by rain breathe more efficiently, their stomata freed of obstructive dust. The chemistry behind this cleansing is quietly elegant, almost poetic in its subtlety. Water molecules are polar, with a slight positive charge at one end and a slight negative at the other. This intrinsic polarity allows them to attract and bind countless types of particles and gases floating invisibly through the air. Some pollutants dissolve readily. Sulfur dioxide, nitrogen oxides and other chemical residues surrender to the embrace of water, vanishing from sight and temporarily from concern. Others, like dust, pollen, soot, or microscopic fragments of ash, are carried along physically, trapped within the invisible spheres of falling rain. Each droplet is a miniature janitor, performing its unseen duties with precision. The end result is the same. The air feels less cluttered, skies become more transparent, and the world, even if just for a few hours, feels quietly renewed, lighter, and cleaner. The scale of this natural cleansing is staggering. A single thunderstorm can remove millions of tons of particulate matter from the atmosphere. Scientists who measure air quality often wait for rain events to reset their instruments, knowing that a downpour temporarily restores a sense of purity to the air. And there is another, more subtle factor enhancing this effect. Negative ions, generated as water droplets, collide with one another and fall through the air. These tiny electrical charges interact with atmospheric particles and may even stimulate a sense of invigoration in human perception. Breathe deep after a fresh rainfall, and you can feel it crisp, clean, almost electric, refreshing in a way that dry, dusty air never can be. Of course, rain's cleaning power has its limits. In heavily polluted regions, the particles it captures do not vanish. They are simply relocated. They accumulate in soils, waterways, urban surfaces, and infrastructure. Acid rain, a particularly potent example, demonstrated that cleaning the air could sometimes shift the problem downward, corroding buildings, eroding statues, and harming ecosystems. Yet even in these scenarios, the principle holds: rain redistributes, rather than destroys, pollutants. Despite these caveats, rain's role as an atmospheric cleaner is profound. It shapes ecosystems by removing dust that might block sunlight or clog plant pores. It affects climate, because atmospheric particles influence how sunlight is scattered and absorbed. It improves human health by temporarily reducing concentrations of fine particulate matter that contributes to respiratory distress. Every shower, from a gentle drizzle to a torrential storm, is a subtle act of maintenance for the planet's atmosphere, a quiet choreography of chemistry and physics at work above our heads. There is a particular poetry in this invisible labor. We see drops striking pavements, rooftops, and fields, but high above, each drop has already been a diligent worker, scrubbing and collecting, restoring balance to the air. The next deep breath after a storm is not simply psychological relief, it is the literal taste of cleaner, clearer skies. Rain's chemistry may not always announce itself dramatically, but it is unerringly thorough, washing the heavens so life below can thrive a little easier, the air carrying a subtle signal of renewal. Rain also transforms the sky into a dynamic canvas. As clouds begin to part and sunlight returns, a rainbow may stretch across the horizon, as if nature had signed its work with a flourish of colour. The phenomenon seems magical, yet its secret lies not in mystery, but in the intricate dance of physics and chemistry within countless tiny raindrops. Each droplet becomes a miniature prism, bending, refracting and reflecting light into its constituent spectrum. When millions of droplets cooperate, they paint the air with arcs of red, orange, yellow, green, blue, indigo, and violet. Sunlight, which appears white to the naked eye, is in fact composed of a multitude of wavelengths, each corresponding to a distinct colour. As this light enters a raindrop, it slows and bends, a process called refraction. This is why a straw appears bent in a glass of water, or why your legs seem oddly foreshortened wading into a pool. Inside the droplet, the light reflects off the inner surface before refracting once again as it exits back into the air. The result of this sequence of bending and reflection is the rainbow, each wavelength dispersing slightly differently, red bending less sharply, violet bending more, spreading white light into a vivid spectrum. Geometry governs its appearance. The angle between incoming sunlight, the droplet, and the observer's eye dictates whether the refracted and reflected light reaches you. Most brilliant rainbows appear when the sun is low on the horizon, typically early morning or late afternoon. Sunlight enters the raindrops at just the right angles, around 42 degrees for red light, slightly less for violet, casting the spectrum back toward the observer. This is why a rainbow cannot be observed at noon when the sun is overhead. In truth, a rainbow is not a fixed object, a singular entity suspended in the sky. It is an optical phenomenon, crafted by countless droplets positioned just right for each viewer. Move a few steps and the rainbow you see is technically a different one, composed of a new set of droplets, uniquely tailored to your position. Sometimes, a second rainbow forms above the first. Known as a double rainbow, it results from light reflecting twice inside the droplet before emerging. The secondary arc forms at a wider angle, around 51 degrees, and its colours are reversed, red on the inner edge, violet on the outer. These rainbows appear fainter because each reflection reduces the intensity of light, but when visible, they add drama and a sense of wonder to the sky. Look closely at the inner edge of a bright rainbow, and you might notice faint, closely spaced bands of colour, supernumerary bows. These delicate pastel arcs arise from the wave nature of light. As light waves overlap and interfere within droplets, they produce additional fringes, a subtle reminder of light's dual character, both particle and wave. Such details reveal that the rainbow is not merely beautiful, it is an intricate illustration of physics, geometry, and chemistry working together in harmony. Raindrop size further influences the rainbow's appearance. Small droplets produce soft, washed-out arcs like pastel brushstrokes across the sky. Large droplets, in contrast, create vivid, sharply defined colors. Heavy showers often give rise to brilliant, intense rainbows, while mist or fine drizzle may form ghostly, pale fogbows, broad white arcs that whisper of color rather than declare it boldly. For centuries, humanity has been captivated by rainbows. Aristotle observed their geometry, medieval scholars debated their spectral formation, and in the 17th century, Isaac Newton famously used prisms to reveal that white light contains all the colors of the spectrum. Through careful experimentation, he demonstrated that rainbows are not painted across the sky by the heavens, but are revealed through the bending, refraction and reflection of light within countless tiny raindrops. Yet even armed with scientific understanding, the sight of a rainbow continues to inspire awe. Its ephemeral nature, lasting only while sunlight strikes droplets at precisely the correct angles, reminds us that beauty is often transient. A passing cloud, a shift in the sun's position, or a change in rainfall can make the rainbow vanish in an instant, and that very transience enhances its allure, a subtle lesson in the fleeting nature of wonders. Rainbows also carry profound and universal symbolism across cultures. They have long been interpreted as signs of peace, hope, reconciliation, and the connection between earth and sky. Legends and myths long preceded scientific explanations, yet their emotional power persists unchanged. Even today, a rainbow can halt conversations, draw gazes upward, and unify observers in silent admiration. It is a rare convergence of science, art, and perception, a vivid demonstration of chemistry, physics, and geometry harmonized in the natural world. Every rainbow you see is the work of millions of raindrops. Each droplet acts as a lens and a mirror, splitting sunlight into its hidden spectrum, creating arcs of color that together form the familiar, mesmerizing bow. Each is a microcosm of physics and chemistry in action. When sunlight and rain meet just so, it is worth pausing to watch the spectacle, to remember that within each shimmering band lies a quiet lesson in the profound power of water, light, and geometry. But before light can dance through raindrops, each drop begins its life as something more than water. Condensation cannot occur spontaneously. Water vapor requires a seed, a nucleus to cling to. These are often tiny fragments suspended in the air: dust, sea salt crystals, volcanic ash, pollen, even microscopic industrial particles. Though minuscule, these specks shape the chemistry of rain and influence the ecosystems below. Each falling drop is more than liquid. It is a courier carrying elements and minerals across the surface of the planet. Consider dust. Winds sweep across deserts and arid plains, lifting fine particles into the atmosphere. The Sahara Desert, for example, is a vast, almost continuous source of airborne dust, sending plumes that travel thousands of kilometers across oceans. When raindrops condense around this dust, they capture its mineral load. When these drops finally descend, they deliver essential nutrients to distant ecosystems. The rain that falls on the Amazon rainforest may carry minerals eroded from the Sahara's sands, replenishing soils that would otherwise be depleted by intense tropical growth. Dust, dispersed via raindrops, becomes a subtle continent-spanning courier of fertility, linking landscapes that could not be more distant. Sea salt plays an equally significant role. Breaking waves fling tiny droplets of water into the air, which then evaporate, leaving behind crystals of salt. These particles, suspended in the atmosphere, act as condensation nuclei for clouds over oceans. Raindrops forming on these seeds carry traces of sodium, chloride, and other ions. When this rain falls back into the sea, the chemistry is largely recycled, but when it drifts inland, it delivers a faint briny seasoning to soils far from the coast, subtly influencing plant health and soil chemistry. Too much salt can harm ecosystems, of course, but in balanced amounts it supports life in ways invisible to the casual observer. Volcanic ash adds yet another layer of complexity. Eruptions release enormous quantities of mineral-rich ash into the stratosphere, where it may remain suspended for months or even years. These particles, carried by wind, eventually seed raindrops across the globe. Volcanic ash is chemically diverse, containing silica, iron, calcium, potassium, and other trace elements. When incorporated into rain, it enriches soils, making volcanic regions some of the most fertile on Earth. Farmers may fear eruptions for their immediate danger, Yet they also understand the long-term boon that follows fertile land nourished by rain, carrying volcanic minerals. All of this contributes to a key realization: raindrops are never chemically identical. Rain over oceans carries salt. Rainfall sweeping over deserts may be slightly alkaline. Rain in forested areas may absorb organic compounds emitted by vegetation. Each shower has its own chemical fingerprint, reflecting the unique particles it encountered during formation and descent. This fingerprint profoundly affects soil fertility. Nitrates generated by thunderstorms fertilize crops. Desert dust replenishes forests. Iron transported in Saharan dust triggers plankton blooms in distant oceans. Each drop is a link in an intricate planetary system, redistributing the essential building blocks of life quietly, persistently, and often unnoticed. Imagine each raindrop as a tiny courier traveling from sky to earth with a miniature package of minerals tucked inside. Some may carry a pinch of desert dust, others a shard of sea salt, others fragments of volcanic glass. When released upon impact, these gifts scatter into soils, rivers, and oceans, nourishing ecosystems across continents. Individually, the cargo seems trivial. Collectively, billions of raindrops deliver a planetary-scale system of mineral transfer. This chemistry also shapes how rain feels and smells. Salt-laden rain from coastal clouds carries a crisp freshness. Dust-rich rain may taste faintly alkaline. Rainfall laden with Saharan dust may stain surfaces with a reddish tint. These variations are visible, tactile, and aromatic proofs of the journey each raindrop has undertaken. The long-distance transport of minerals through rain is a constant reminder of the Earth's interconnectedness. A shower in the Amazon may owe its fertility in part to winds in Africa. Crops in Europe may receive vital nutrients borne across the Atlantic. Even the clarity of a remote alpine lake can be influenced by volcanic ash deposited halfway around the globe. Not all of this transport is beneficial. Alongside natural minerals, raindrops may carry pollutants, heavy metals, industrial residues, soot, or chemical byproducts. These unwelcome guests are redistributed with the same efficiency as natural nutrients, sometimes with detrimental consequences for ecosystems. Acid rain, for instance, demonstrated how rain's cleansing power can also become a burden, removing pollutants from the sky, only to deposit them into soils, lakes, or the surfaces of buildings, corroding stone and metal over time. Yet even in these cases, the underlying principle remains the same. Each raindrop is a vehicle, carrying far more than water. Each one connects the atmosphere to the biosphere, delivering a cargo that may nurture or challenge life below. When we consider rain from this perspective, the sky transforms from a passive reservoir of water into a vast, intricate network of couriers. Millions upon millions of droplets travel daily from cloud to earth, each with its own chemical fingerprint, each distributing minerals, salts, dust, or organic compounds collected on its journey. Some drops feed the dense canopies of forests, replenish rivers, or refresh oceans. Others carry whispers of distant deserts, the remnants of volcanic eruptions, or traces of industrialized cities. Collectively, these countless drops maintain the dynamic chemistry of our planet, ensuring no ecosystem exists in isolation. Each drop that splashes onto a leaf, trickles into soil, or merges into a river tells a story written in dust, salt, and minerals. Raindrops are not merely water, they are messengers delivering fragments of earth back to earth, sustaining life in a continuous cycle of nourishment, renewal, and transformation. The water we see falling as rain today has been on Earth for billions of years. No molecule is truly new. It moves, shifts, and transforms through a cycle that is at once ancient and endlessly repeated: the global water cycle. This cycle is deceptively familiar, yet profoundly complex, connecting oceans, clouds, glaciers, rivers, soils, and even the atmosphere above our heads. At its core lies chemistry. The bending of bonds, the dissolving of gases, the transformation between liquid, vapor, and ice. Rain is merely the most visible stage of this ongoing process, the moment when the sky returns what it borrowed, delivering water to the world below. The journey begins with evaporation. Sunlight energizes surface water, whether from oceans, lakes, or rivers, imparting enough energy for molecules to escape the liquid phase and rise as vapor into the atmosphere. This seemingly invisible ascent is actually a massive daily migration. Even the slow release of moisture from cold lakes or the steady evaporation from soil contributes to this global reservoir. Plants participate through transpiration, releasing water vapor from their leaves as they photosynthesize and respire, feeding the atmosphere with yet more moisture. Once in the sky, the water vapor cools with altitude. Molecules that had once raced across the surface of oceans lose kinetic energy and begin to coalesce. Condensation occurs, often facilitated by tiny particles of dust, salt, pollen, or ash. Water molecules gather around these nuclei to form droplets, which collectively create clouds, the visible, floating symbols of Earth's hydrological dance. Clouds may appear fluffy and light, yet they contain vast quantities of water, suspended against gravity by rising air currents. Eventually, the weight of accumulated droplets overcomes the updrafts and precipitation begins. Raindrops, snowflakes, or hailstones fall, each delivering water back to Earth's surface. These droplets are couriers, each carrying both life-giving water and the chemical and mineral cargo they picked up along the way. Some drops may nourish crops with nitrogen from lightning-generated nitrates. Others may replenish soils with minerals from dust or volcanic ash. Each drop is part of a planetary scale exchange, a constant redistribution of matter and energy. The remarkable aspect of this system is its continuity across eons. Many molecules in a raindrop today have been traveling for millennia. Some may have fallen on the back of a dinosaur, been locked in ice for thousands of years, or drifted across oceans countless times. A single molecule may spend centuries in a glacier, only to melt, flow through rivers, evaporate, and return to clouds again. The water cycle has no beginning and no true end, only movement, transformation, and endless circulation. The rain we feel is both present and ancient, connecting us to all life that preceded us. Each drop carries whispers of ages past, reminding us that the water sustaining life today has already been part of countless ecosystems, continents, and climates. Chemistry governs every stage of this cycle. Water's polarity allows molecules to bond and unbond with ease, enabling it to transition between liquid, vapor, and ice with small energy shifts. Carbon dioxide dissolves into rain to create mild acidity, slowly weathering rocks and releasing minerals into soils and rivers. Ice forms with a crystalline lattice, stabilized by hydrogen bonds, creating a structure less dense than liquid water, a rare and crucial property that allows lakes to freeze from the top down, preserving life below. Without these chemical peculiarities, the water cycle would be radically altered. The cycle is also a key climate regulator. Evaporation removes heat from oceans and land, cooling surfaces, while condensation and precipitation release stored heat into the atmosphere, powering weather systems and distributing energy globally. Rain is thus a conduit not only for water but for energy, linking local weather events to planetary systems. Each storm, each drop, is part of a vast exchange that balances temperature, drives winds, and fuels clouds that shade the earth below. There is a poetic truth in this. Every raindrop carries an ancient memory. When it splashes on your hand, you may be touching water that once flowed through the canyons of prehistoric landscapes, dripped from the leaves of ancient forests, froze in glaciers, or fell from early Earth's first clouds. Some molecules may even predate the planet itself, arriving via icy comets that seeded Earth's oceans billions of years ago. Rain is in essence a traveler across deep time. It is more than moisture. It is the continuity of Earth's history made tangible in a single moment. The global water cycle is both relentless and delicate. It never ceases, tirelessly moving water between sky, land, and sea, a process as ancient as the planet itself. Yet even slight perturbations, shifts in temperature, wind patterns, or atmospheric chemistry can alter its rhythm, redirecting rainfall, intensifying droughts, or swelling rivers. For life on Earth, this cycle is foundational. Crops rely on consistent rainfall. Rivers carve and sculpt landscapes over millennia. Oceans circulate heat across the globe, and through it all, the chemical properties of water, the polarity of its molecules, the ability to dissolve gases, the unique hydrogen bonds, bind the system together. Rain is the visible signature of this grand process, the tangible moment when the sky returns its gift to the earth, carrying not only freshness, but also the echoes of a history that spans continents, epochs, and millennia. To watch a rainfall is to witness chemistry and physics in motion, a fleeting yet profound glimpse of Earth's endless cycles. Each drop is a messenger, delivering nutrients, energy, and memory. It nourishes forests, replenishes aquifers, shapes rivers, and cleans the air. It reminds us that nothing on this planet is truly isolated. All life is connected through the silent work of water, traveling ceaselessly, quietly sustaining life on scales both microscopic and planetary. The impact of a single drop may seem small, yet billions of such droplets cascade through clouds to create the atmosphere to Earth exchanges that underpin ecosystems, climates, and human existence. Even more remarkable is rain's role in the origin of life itself. Billions of years ago, the young Earth was a restless, stormy world. Rain fell not on lush fields or forests, but onto bare rock, steaming volcanic plains, and shallow pools of primordial water. Into these early receptacles, raindrops may have delivered the raw ingredients that eventually gave rise to living cells. Seen in this light, rain is not merely a meteorological event, it is one of the planet's oldest chemists. In the early atmosphere, conditions were drastically different from today. The air was thick with methane, ammonia, hydrogen, and water vapor. Volcanoes erupted with carbon dioxide and sulfur compounds. Storms were frequent and violent, and lightning forked ceaselessly across the skies, splitting molecules apart and allowing them to recombine in novel ways. Rain swept these products down into shallow pools, gathering them into miniature chemical laboratories on the Earth's surface. Scientists have long pondered how simple molecules arrange themselves into the complex structures of life. A groundbreaking experiment in the 1950s offered a hint. Stanley Miller and Harold Urey recreated what they believed to be the early Earth's atmosphere in a laboratory. Their apparatus contained methane, ammonia, hydrogen, and water vapor, zapped repeatedly with electrical sparks to simulate lightning. After a week, the water at the bottom had darkened, and analysis revealed amino acids, the building blocks of proteins, had formed spontaneously. This showed that energy from lightning and chemical ingredients from rain could generate complexity from simplicity. Once deposited into pools, these molecules could accumulate, forming rich chemical soups. In shallow waters, cycles of evaporation concentrated them further, allowing molecules to link into chains, eventually giving rise to proteins, nucleic acids, and self-replicating systems. Rain was not merely a delivery system but a concentrator, a stage setter creating conditions ripe for life. Water itself is uniquely suited for this role. It allows molecules to collide, interact, and disperse, yet can also dilute chemicals excessively. Rain, by filling small pools and then partially evaporating under the sun, created cycles of concentration and dilution, cycles now thought crucial for forming long molecular chains, such as RNA and DNA. In essence, early rainfall may have stirred the pot, repeatedly filling and drying primitive ponds until complexity emerged. Not all scientists agree on the exact origins of life. Some propose deep-sea hydrothermal vents, icy environments, or even the delivery of organic molecules via comets. But in almost all scenarios, rain likely played a supporting role, shaping the atmosphere, redistributing materials, and delivering energy and chemicals across the planet. Its influence was widespread. Wherever life's ingredients accumulated, rainfall helped move them into place, connecting sky, land, and sea in a dynamic chemical dialogue. Imagining the first rains is to conjure a world unlike our own. There were no forests or fields, only bare rock, volcanic craters, shallow seas, and barren plains. Storms were violent, filled with sharp smells of sulfur and ammonia, yet each droplet carried potential, ferrying molecules that could become life. That perspective extends even beyond Earth. On Titan, Saturn's largest moon, rain falls not as water but as liquid methane, shaping landscapes in alien chemistry. Venus experiences droplets of sulfuric acid, which evaporate before reaching the surface. Astronomers speculate that some exoplanets may even experience rains of molten iron, glass, or hydrocarbons. Rain, it seems, is a universal process, wherever an atmosphere and liquid coexist. On Earth, it may have helped build life. Elsewhere, it could play analogous roles, orchestrating chemistry under entirely different conditions. Today, rain continues to shape life in subtle and profound ways. It hydrates plants, activates soil microbes, distributes nutrients, cleans the air, and connects ecosystems over vast distances. Dust from deserts, salts from oceans, and ash from volcanoes are carried by raindrops across continents, replenishing soils and sustaining life far from their origin. Nitrogen fixed by lightning is transported to plants, sustaining forests and grasslands. Even pollutants are redistributed by rainfall, reminding us that every raindrop is a vehicle capable of both benefit and harm. Yet the principle remains: rain is a messenger, connecting the atmosphere and the biosphere, shaping ecosystems quietly but profoundly. Every shower is a conversation between sky and soil, droplets and leaves, chemistry and life. One of the most important chemical gifts of rain is nitrogen in a usable form, supporting plant growth. Alongside nitrogen, rain delivers minerals such as calcium, magnesium, potassium, and trace elements critical for microbial and plant metabolism. This invisible delivery system sustains food webs, influencing everything from the tiniest algae in oceans to the largest terrestrial mammals. Each drop is a tiny courier, ferrying nutrients, chemicals, and energy, linking deserts, oceans, volcanoes, forests, and human settlements into a dynamic, interconnected global system. Rain is also a remarkable orchestrator of physical processes. Its impact sculpts soil and rocks, carves riverbeds, and moderates climates by transporting heat from evaporation and condensation. Its chemistry affects acidity, mineral content, and even the scent of the air. The smell of post-storm rain, known as petrichor, arises from oils released by plants and the action of actinobacteria in the soil, another subtle signature of rain's chemical influence. Every sensory experience of rainfall is underpinned by a web of chemical and physical interactions, linking the microscopic world of molecules to the macroscopic experience of life. In sum, rain is far more than simple moisture. It is a messenger of chemistry, a sculptor of landscapes, a conveyor of nutrients, and perhaps one of life's oldest collaborators. Each drop carries the weight of history, the power of chemistry, and the potential for life itself. To stand in a gentle shower or watch a drizzle slide down a window is to witness the silent, ongoing work of the planet. water cycling between sky, land, and sea, molecules moving, colliding, and interacting, life sustained in ways both visible and invisible. The rain we experience today nourishes crops, replenishes rivers, and cleanses the air. Yet each droplet may also be an echo of the earliest chemical experiments that coaxed life from prebiotic chemistry. Rain is at once ancient and present, simple and complex, mundane and miraculous, a continuous testament to the interconnected chemistry of Earth. The atmosphere around us is rich in nitrogen gas, yet it is locked in a form, noether, that is extraordinarily stable. Plants cannot break this bond themselves. Rainstorms, especially those accompanied by lightning, perform the difficult work of splitting nitrogen atoms and binding them with oxygen to form nitrates. These nitrates dissolve in raindrops and descend to the soil, where they become accessible to plant life. For plants, nitrates are like gold, the raw materials from which amino acids, proteins, and nucleic acids are built. Every leaf, stem, and seed relies on nitrogen, and rainfall is one of the planet's quiet couriers, delivering it invisibly and efficiently. Alongside nitrogen, rain carries dissolved carbon dioxide. As droplets fall through the atmosphere, they absorb CO2, or forming a weak solution of carbonic acid. This mild acidity enriches soil with carbonates that both plants and microbes can use. In some cases, the CO2 also helps buffer soil chemistry, keeping nutrient cycles stable and enabling ecosystems to thrive. Even oxygen present in the air dissolves slightly into rain. When raindrops reach the ground, they help aerate the upper layers of soil, improving conditions for root respiration and microbial activity. The benefits of rain to plant health extend far beyond dissolved nutrients. Rain physically washes leaves, removing dust, pollen, soot, and other particulate matter that accumulates during dry periods. A plant's leaves act as solar panels, converting sunlight into chemical energy through photosynthesis. Dust on leaf surfaces can reduce efficiency, shading cells and clogging stomata, the tiny pores through which plants exchange gases. A thorough rain is like a restorative cleaning service, returning leaves to their full operational capacity. After a storm, the canopy often appears brighter, the green more vivid, not only from the water's reflective sheen, but also because the leaves are freshly polished for photosynthetic work. Rain also governs the delicate balance of moisture in soil. Roots require a precise ratio of water to air within the spaces between soil particles. Too little water and roots cannot absorb nutrients efficiently. Too much, and oxygen is displaced, suffocating them. Gentle rainfall is especially effective at soaking deeply into the ground, replenishing water reserves without drowning the root systems. Heavy downpours, on the other hand, can compact soils or cause runoff that carries nutrients away. Even in these extremes, the water cycle is reset and life continues its negotiation between abundance and scarcity. Plants themselves are far from passive recipients of rainfall. Many species have evolved chemical responses to moisture. Hormones such as auxins and cytokinins are activated by water absorption, triggering bursts of growth after soaking rains. Desert plants, for instance, may remain dormant for months, then erupt into bloom after a storm, responding to sudden availability of both water and dissolved nutrients. Farmers frequently observe similar phenomena. Crops can visibly perk up within hours of rain, not merely because of hydration, but due to intricate internal chemical signaling that coordinates growth. Seeds, too, are attuned to rainfall. The earthy scent humans call petrichor arises partly from oils secreted by plants and actinobacteria during dry periods. These oils accumulate in soils and rocks, remaining dormant until rain arrives, releasing them into the air. Petrichor may also serve as a chemical cue for seeds. In some species, these compounds signal that conditions are now favorable for germination. Seeds that might remain dormant for years detect the presence of rain and awaken, sprouting into new life. Rain thus carries a chemical message across generations, announcing now is the time to grow. The choreography of plant response extends even to stomata. During dry spells, these tiny openings on leaf surfaces close to conserve water. When rainfall replenishes soils, plants can afford to reopen stomata wider, allowing carbon dioxide to flood in for photosynthesis and enabling transpiration, the release of water vapor, which cools the leaf and regulates temperature. In this way, a single rainfall resets the balance of plant physiology. Rain's influence radiates outward to entire ecosystems. As nitrates, carbonates, and trace minerals arrive in the soil, plants grow more vigorously, producing more leaves, stems, and roots. These healthier plants release greater amounts of oxygen into the atmosphere, provide more sustenance to herbivores, and ripple through food webs to support carnivores. In this way, the chemistry of a single shower can cascade through entire forests, meadows, and agricultural systems. Human agriculture has long relied on this natural fertilization. Before synthetic fertilizers, farmers depended on the nutrients delivered by rain. Even today, rainwater is often preferable to irrigation water, containing a more balanced mix of nutrients and fewer salts. Gardeners regularly observe plants appearing greener and more vibrant after rainfall than after artificial watering, a phenomenon confirmed by scientific study. Beyond terrestrial life, rain exerts a profound influence on the oceans. At first glance, raindrops falling into the sea might seem trivial, adding only a few milliliters of fresh water to a vast saline expanse. Yet even this small addition carries outsized significance. Each drop contains dissolved gases, minerals and organic compounds that subtly alter surface salinity, nutrient distribution, and microbial activity. By creating a freshened layer at the air-sea interface, raindrops affect the behavior of phytoplankton and other microorganisms that form the foundation of marine food webs. The ocean's salinity itself is the product of eons of chemical exchanges, and rainfall continues to mediate this delicate balance. Rain is, therefore, both an agent of life and a sculptor of planetary chemistry. Each drop is a messenger, a conveyor of nutrients, a chemical signal, a cleanser, and a catalyst. Its effects reach from the tiniest seed buried in soil to the largest forest canopy, from a quiet meadow to the vast expanse of the open sea. Rainwater carries not only hydration, but a complex cocktail of chemical information, coordinating growth, resetting physiological systems, and linking ecosystems across continents. Every falling drop tells a story of nitrogen forged by lightning, of carbon dioxide absorbed from the air, of salts and minerals carried from deserts or oceans, and of chemical signals that awaken seeds and refresh plants. Rain is not merely weather, it is an enduring chemical dialogue between sky and earth, a conversation ongoing for hundreds of millions of years, quietly sustaining life with every droplet. Seawater averages about 35 grams of dissolved salts per litre, a concentration marine life has adapted to with exquisite precision. Rainwater, by contrast, is fresh. When it falls on the ocean, it forms a thin, temporary layer of lower salinity at the surface, a lens of freshened water. Though often only a few centimeters thick, this lens matters profoundly for the microscopic organisms living at the interface of air and sea. Fresh water floats because it is less dense than saline water, and it can persist for hours or even days depending on winds and currents. This subtle dilution alters the exchange of gases between ocean and atmosphere. Carbon dioxide, oxygen, and other gases move differently across a freshened surface, meaning rain actively modulates the chemical interface through which the ocean breathes. Raindrops also deliver their own chemical cargo. As they fall, they pick up gases such as CO, nitrogen oxides, and sulfur compounds. They may also carry particles of dust, pollen or sea salt that initially helped form the drops. When these drops meet the ocean, they transfer this cargo to surface waters. Some contributions are pollutants, but many are nutrients. Dust particles rich in iron, for instance, are known to stimulate plankton blooms in nutrient-poor regions of the ocean. In this way, rain acts as a courier, transferring elements from the land and sky into the ocean's chemical machinery. The impact of rain is especially noticeable in tropical waters, where sudden downpours are frequent. Heavy rainfall creates stratified layers, a fresh layer on top and saltier water below. While stratification can temporarily limit vertical mixing, it stabilizes the upper water column, keeping phytoplankton in the sunlit zone where photosynthesis is most effective. When nutrients are present, these conditions can trigger rapid blooms that fuel the base of the marine food web. Conversely, strong storms combine freshening with vigorous wind and wave action, mixing nutrient-rich deep waters into the surface layer. This interplay of dilution and mechanical stirring creates a chemical reset, redistributing essential elements such as nitrogen, phosphorus, and iron. In some cases, plankton blooms become so dense that they are visible from space as swirls of green or turquoise, a reminder of rain's invisible yet transformative influence. Rain chemistry varies depending on location. Over the open ocean, rainfall is relatively clean, carrying mostly sea salt and dissolved gases. Near coasts or industrial regions, however, raindrops may contain higher concentrations of pollutants, including sulfur and nitrogen compounds that can contribute to ocean acidification. While a single drop seems insignificant, the cumulative effect is profound, particularly in enclosed seas or estuaries where dilution occurs slowly. In this sense, rain is both a reflection of natural processes and a mirror of human activity, a delivery system for nutrients and contaminants alike. Plankton, the drifting foundation of marine ecosystems, are particularly sensitive to these chemical nuances. Certain species flourish in the slightly diluted, nutrient-enriched surface waters following a storm, while others are stressed by rapid salinity changes. Phytoplankton respond quickly to the nutrients delivered by rain, and their growth supports zooplankton, small fish, and ultimately entire marine food chains. Even air-breathing marine animals, such as dolphins or seabirds, feel the indirect effects. Changes in plankton abundance influence fish stocks, which in turn affect predator populations. Fishermen have long observed seasonal patterns linked to rainstorms, noting that certain rains herald productive fishing periods, a subtle connection between meteorology, chemistry, and ecology. Rain's relationship with the ocean is not only scientific, but profoundly poetic. For sailors throughout history, a sudden shower at sea was more than a meteorological event. It was salvation. Amid the endless salt of the waves, rain offered drinkable water, collected in barrels or caught in cupped hands. On small islands, it filled cisterns and sustained entire communities. This duality, fresh from above, saline below, remains one of the most striking aspects of rain's role over the sea. With every shower, new water meets ancient water, their mingling producing temporary layers, subtle exchanges, and chemical transformations. From a planetary perspective, these meetings are part of a grand balancing act. The ocean constantly surrenders vapor to the sky, and clouds in turn return it as rain enriched with dissolved gases and minerals. Through this cycle, the oceans remain full, active, and alive. Each raindrop is far from anonymous. It is a courier binding atmosphere, sea, and life itself. Humans have long recognized rain's importance, even when its chemistry was a mystery. Before meteorology could chart storm systems or chemistry could name molecules, people saw in rainfall the hand of gods or spirits. Agrarian societies depended on seasonal showers, and drought could bring not only hunger, but collapse. Thus, rain became blessing, curse, mystery, and divinity. In Greek mythology, Zeus wielded thunder and rain as both favor and punishment. In Mesopotamia, the storm god Adad commanded the waters that sustained the fertile valleys of the Tigris and Euphrates. In Hindu tradition, Indra's thunderbolt was both weapon and key, unlocking life-giving rain. Each myth reflected a truth: water sustains life and rainfall determines survival. To invite rain, people turned to ritual. Across North America, Native American tribes performed intricate rain dances, accompanied by music, rhythm, and symbolism. These were not idle superstitions but deeply rooted practices, expressing respect for natural cycles and a yearning for harmony with forces beyond human control. In parts of Africa, sacred ceremonies during drought included chants, offerings, and community gatherings aimed at persuading the heavens to open. Similar traditions flourished across Asia and South America, each blending cultural meaning with practical need: water for crops, herds, and families. Without the language of molecules, people still sensed rain's dual nature: its power to nourish and its ability to reshape soil, taste, and fertility. Some even linked rain with lightning, intuitively grasping that storms renewed the ground. What science would later describe in terms of nitrogen fixation, ancient communities captured in stories, dances, and faith. As civilizations grew, so did their understanding of rain's blessings and perils. Nowhere is this clearer than in the monsoon of South Asia, a cycle still shaping economies and lives today. When timely, the monsoon delivers prosperity, swelling rivers, irrigating fields, and feeding millions. When late or absent, it brings drought and famine. When violent, it unleashes floods that devastate villages and wash away entire harvests. The monsoon remains a living reminder of rain's double-edged nature, essential yet dangerous. Ancient records from China's dynasties, Egypt's kingdoms, and Mayan city-states all testify to cycles of abundance and hardship, bound to rainfall. Entire civilizations rose where rains were steady and faltered where they failed. The Industrial Revolution introduced a new chapter. As coal furnaces roared and smokestacks filled the skies with soot, people began noticing that rain itself had changed. By the mid-19th century, chemist Robert Angus Smith coined the term acid rain, describing precipitation that corroded stone, weakened forests, and poisoned lakes. The culprit was clear: sulfur dioxide and nitrogen oxides from factories and engines dissolving into raindrops, forming acids stronger than natural carbonic acid. The evidence was everywhere: blackened monuments, skeletal forests, fishless waters. Rain had become a mirror of the atmosphere, carrying humanity's emissions back to Earth. Yet the story of acid rain is not only a warning but also a rare environmental success. Awareness grew, and by the late 20th century, nations began acting. The Clean Air Act in the United States, treaties across Europe, and technologies like smokestack scrubbers and catalytic converters curbed emissions. Slowly, rain grew less acidic, lakes and forests began to recover. Acid rain remains one of the first global environmental crises where collective action reversed the damage, a reminder that while human activity can warp the chemistry of rain, human effort can also repair it. Beyond industry, rainfall has never lost its central role in agriculture. Farmers, like their ancestors, still watch the skies with hope and worry. A well-timed rain brings abundance, while drought devastates and flooding destroys. Agricultural calendars have been structured around rainfall for millennia, and some of humanity's earliest technologies, irrigation canals, cisterns, and reservoirs, were inventions to manage water when the heavens could not be trusted. Today, satellites and climate models attempt to forecast rainfall with precision, entire economies hinging on the accuracy of these predictions. Yet despite all our tools, the awe remains. Even now, when a sudden shower cools a city street, or the first drops darken dry soil, people pause. The scent of petrichor, the arc of a rainbow, the hush of falling rain. These sensations remind us that rain is more than data on a radar screen. Rituals may have changed, but reverence lingers. Rain connects us to ancestors who once danced for it, to farmers who prayed for it, and to scientists who study its chemistry today. It has been divine, destructive, and deeply practical all at once. Each drop that descends from the sky carries echoes of centuries, of civilizations rising and faltering, of myths whispered and scientific truths uncovered. Rain is never only water. It is weather, it is chemistry, it is memory and culture interwoven in a delicate veil that drifts downward. To step into it, to let it touch your skin, is to join an ancient ritual that has stretched across every generation since the dawn of agriculture, when human eyes turned upward with the same blend of hope, dread, and wonder. Rain has long been imagined as a cleanser, rinsing the dust from streets, polishing leaves until they shine, leaving behind the cool perfume of freshness. Yet the raindrops of our modern world are not always so innocent. As they pass through the atmosphere, they gather what lingers there: traces of exhaust from engines, soot from factories, smoke from wildfires. Each drop becomes a collector, a tiny courier carrying its fragile cargo down to the soil, the rivers, the stones of the city. Urban skies heavy with nitrogen oxides, sulfur compounds, volatile organics, and fine particulates weave clouds that are no longer pure. Raindrops born from such skies descend carrying the breath of industry, the residue of fuel, the shadow of our machines. In this way, rainfall has become a mirror, reflecting not only the cycle of nature, but the story of our own restless activity. The difference between a shower in a mountain valley and one over a crowded city can be startling. Measurements confirm what the eye sometimes sees. Rainfall over polluted regions carries higher concentrations of contaminants than the gentle rains of remote islands or open seas. At times, this contamination even reveals itself in color. Brown rain, darkened with soot or dust, has been known to stain clothing, stone, and skin. In the days of coal's dominance, such rainfall was commonplace, falling like a dirty veil across towns and factories, blackening everything it touched. Even in more recent decades, storms sweeping up desert dust or smog have carried down yellow and ochre-tinted rains. These discolored showers remind us vividly that raindrops are not anonymous. They are tiny vessels bearing in their descent whatever has floated above, and what they carry matters. Soot-laden precipitation is not only an inconvenience for laundry lines or polished marble. When it lands on snowfields, the dark particles absorb sunlight, hastening the melt of glaciers. When it seeps into streams and lakes, the chemical load can stress or even extinguish aquatic life. In soils, the acids formed from polluted rain can leach away essential minerals while leaving behind harmful compounds. The simple journey of a raindrop through a tainted sky reshapes landscapes and ecosystems in subtle yet lasting ways. Climate change has added further complexity to this already intricate chemistry. Warmer air, capable of holding more vapor, drives heavier downpours in some places and deep droughts in others. The altered rhythms of evaporation and condensation reshape where and how pollutants are washed back to Earth. Wildfires, now more frequent and intense, release torrents of soot and organic aerosols into the air. Raindrops falling through smoke-heavy clouds arrive infused with the chemistry of burning forests, carbon compounds, trace metals, microscopic ash. Even what we call natural rain is no longer free of the human hand. At the heart of these changes are aerosols, the invisible seeds of clouds. Tiny particles suspended in the air determine whether raindrops form at all, and they dictate much of their chemistry. In pristine air, sea salt, dust, or volcanic ash provide simple natural nuclei. In polluted atmospheres, The particles are stranger: sulfates from smokestacks, nitrates from engines, black carbon from fires. These alter not only the acidity of the rain, but the pathways of storms themselves. Scientists today can trace the fingerprints of entire industries or regions within the chemical patterns of rainfall, reading storms as one might read ancient scrolls. And yet, this story is not solely one of decline. There have been moments of renewal, of deliberate care reshaping the skies. When the term acid rain was first coined in the 19th century, it was a warning. By the late 20th century, the warning had become urgent as forests weakened and lakes emptied of fish. But treaties were signed, scrubbers added to smokestacks, cleaner fuels adopted. Slowly, the chemistry of rain shifted back. Lakes in North America and Europe began to recover. Forests grew stronger, and rainfall softened from its corrosive edge. Cleaner skies gave birth to cleaner rain. The lesson was plain: what we do to the air writes itself into the water that falls upon us. Still, the progress is uneven. In many regions, pollution continues to rise, and rain reflects this imbalance with perfect honesty. A shower in a forest may carry the sweetness of pine and the trace of sea salt. A shower in an industrial corridor may descend with a bite of acid. Rainfall is, in this sense, a daily report card from the sky, telling us how we are tending to the breath of the planet. And yet, no matter its chemistry, each drop retains the same timeless role. It binds the earth to the sky, nourishes the soil, feeds the rivers, renews the seas. Whether tinged with soot or pure as mountain dew, rain participates in the vast circulation of water that has shaped this planet for eons. It remains teacher and mirror. Teacher because it shows us the workings of chemistry, of cycles, of resilience. Mirror because it reflects our actions, pure or tainted, careless or careful. To walk in the rain is to remember that what falls on our heads does not end its journey upon the skin. It seeps slowly into the soil, winding through roots and stones, slipping into hidden streams that feed rivers, and from there it is drawn back into the sky as vapor. Every drop circles endlessly, returning in the next storm. Every decision we make, what fuels we burn, what air we breathe, returns as well, delivered softly upon us. Drop by drop, rain is not distant. It is not separate. It is us, falling back upon ourselves in a gentle reminder of cycles older than memory. Yet liquid rain is only one gift clouds bestow. When the air cools, when temperatures sink low enough, the same molecules take on new shapes and textures. Water does not always descend as liquid. Sometimes it drifts lazily as snowflakes, each one a fragile star. Sometimes it hardens into hailstones, rattling against rooftops with sudden violence. Sometimes it slides invisibly through layers of warm and cold air, arriving at the ground as freezing rain that coats branches, wires, and roads in treacherous glass. All of these forms are simply water, yet each one is transformed by delicate changes in chemistry and physics. Snow is perhaps the gentlest of these transformations. At the heart of every flake is the unique geometry of the water molecule itself. Two tiny hydrogens bent toward a single oxygen, their polar charges encouraging bonds that lock into six-sided patterns. From this simple arrangement emerges endless variety. No two flakes are identical because every moment of growth, every change in temperature or humidity, guides the crystal in a slightly different way. Some fall as delicate stars, others as slender needles, others as flat, simple plates, but all obey the same hexagonal law written into water's structure. Each flake is both fleeting and eternal, vanishing as it melts, yet preserving in its form the history of the cloud that birthed it. Scientists who study ice cores in the polar regions read these frozen crystals as time capsules, reconstructing climates, hundreds of thousands of years past from the bubbles of ancient air locked within. Thus snow is not only a present beauty, but an archive, a record of Earth's memory written in ice. Hail, by contrast, is born in turbulence, supercooled droplets. Liquid water chilled below freezing collide with tiny particles or embryonic ice crystals within a storm cloud. Each collision triggers a freeze, and the newborn pellet of ice is tossed upward by fierce updrafts to meet more droplets, layering upon itself like a pearl growing its shells. Up and down it travels, rising, falling, rising again, until its weight becomes too great for the cloud to hold. When at last it falls, it may arrive as small beads that bounce harmlessly, or as heavy spheres large enough to shatter glass. Slice a hailstone open, and its layers tell the story of those journeys, like the rings of a tree recording time inside a thunderstorm. Freezing rain lies somewhere in between, at once subtle and dangerous. Drops fall as liquid through a warm layer of air, only to pass through a shallow layer of sub-freezing air near the ground. They remain liquid, supercooled and waiting, until they touch a surface. Then, in an instant, they transform, clinging as smooth, hard ice. The world is remade overnight, branches bowed under glittering coats, roads polished into treacherous glass, wires sagging with crystalline weight. Unlike snow, which insulates, or hail, which pounds, freezing rain silences the landscape, encasing it in brittle stillness. Each frozen form of precipitation is born of the same HASO molecule, yet each behaves differently, shaped by thin slices of temperature and pressure. Snow comforts, hail destroys, freezing rain threatens with fragile beauty. All are expressions of the same chemistry, revealing water's ability to shift endlessly, sculpting the earth in forms as soft as lace or as violent as stone. To watch snow drift, to hear hail rattle, to see trees bent beneath icy glass, is to witness chemistry unfolding in crystal form. And yet, whether as flake or stone or frozen glaze, these drops remind us of the same truth. Water is a traveller. Every form it takes tells a story of the air it passed through, of the particles it encountered, of the world it touched on its descent. A raindrop in the forest tells one story. A raindrop in the city tells another. At first glance they look alike, but chemistry whispers their differences. One carries soot and industrial residues, sharpened with acidity. The other holds oils from leaves, traces of pine and earth, softened by the living canopy it has brushed against. In cities, the air is crowded with human breath and machinery. Vehicles release nitrogen oxides, carbon monoxide, and a haze of fine particles. Factories and chimneys add sulfur compounds, while daily life sheds invisible dust from construction, stone, even tires and brakes. Raindrops falling here cannot avoid this atmosphere. They gather it, mix with it, descend altered by it. By the time they reach pavement, they are often more acidic, their pH lower than the mild 5.6 of natural rain. Over centuries, this sharper chemistry has etched stone, blurred the faces of statues, and worn away at marble facades. City rain, though it refreshes, also corrodes. In forests, by contrast, the sky and trees converse in a different language. Leaves and bark release organic compounds, terpenes from pines, isoprene from broadleaf trees, countless other volatiles that scent the air. These act as seeds for clouds, giving vapor something to cling to. Raindrops here carry the signatures of plants and soils, their chemistry softer, more nourishing. As they tumble through branches, they wash away dust and pollen, carrying them gently to the soil below. The result is not only cleansing, but enriching. Soil microbes stir awake, roots drink deeper, and the post-rain air fills with petrichor, the earthy perfume made stronger by oils, and geosmin released from the living ground. It is not merely the illusion of freshness, it is chemistry made fragrant. The contrasts ripple outward, widening with every drop that falls. In cities, rainfall is a restless visitor. It stresses plants already struggling in compacted soils, leaches nutrients that roots can barely hold onto, and etches glass with thin veils of soot and grime. Pavements darken not with purity, but with a film of residues, carrying the signatures of traffic, chimneys, and industry. In forests, the same water tells a gentler story. It seeps into the soil like a gift, feeding nutrient cycles, awakening microbial networks, and sustaining biodiversity with each passing shower. A single downpour can rouse fungi from dormancy, wash minerals deeper into roots, and trigger the quiet respiration of countless organisms beneath the forest floor. Even the raindrops themselves behave differently depending on where they fall. Urban showers often scatter as countless tiny droplets, misty and fine, each born from the density of aerosols suspended in city air. The rhythm is hurried, metallic, rattling against asphalt and rooftops in sharp staccato. Forest rain arrives slower, larger, with droplets that descend heavily through canopies. They tap against leaves, thud into moss, and seep into loam with a deeper, more deliberate rhythm. One can hear the difference, the harsh percussion of rain on concrete versus the softened, almost musical cadence of water on bark, branch, and fern. Forests go beyond receiving rain, they help summon it. Through transpiration, trees exhale invisible rivers of vapor, releasing moisture drawn up from roots into the open air. This vapor feeds cloud formation overhead, creating reservoirs of skybound water that will later return as rain. In this sense, a forest is both source and recipient, breathing out clouds that later fall back upon its soil. The aerosols trees emit, organic compounds such as terpenes, isoprene, and other volatiles, serve as condensation seeds, tiny scaffolds around which droplets can gather. Each shower that falls is in part the forest calling water back to itself, completing a cycle of breath and renewal. Cities tell a different story. Their heat islands distort local rainfall patterns, warming air and altering convection currents. Their polluted aerosols reshape clouds, sometimes suppressing rainfall entirely, other times encouraging sudden, intense downpours. Urban skies, heavy with engineered particles of soot and dust, may seed rain that falls abruptly, overwhelming storm drains, then vanish as quickly as it came. Where forests sustain a steady cycle of exchange, cities disrupt with bursts and absences. From a human perspective, this difference is not just measured but felt. To walk through a city in the rain is to be brushed with grit, to taste faint metallic tangs of exhaust carried within each droplet. The rain smells of engines, smoke, and stone. To step beneath a forest shower is to be cleansed instead. Air cooler, scents sharper, drops softer, even when they are large. The fragrance is green, earthy, invigorating, laced with the perfume of leaves and the ancient oils of trees. Both are water, both are hatho, yet they are water shaped by their journeys. One touched by machines and smoke, the other by soil and leaf. At its core, this contrast reminds us that raindrops are never detached from us. They fall through the world we have created, carrying fragments of it back down. Cleaner skies bring cleaner rain, whether above a metropolis or a forest glade. Forests, with their quiet ability to generate their own chemistry, show a template for balance. Air filled with organic compounds that seed clouds naturally, rain that nourishes instead of corrodes, cycles that restore rather than erode. Every raindrop is a chemical diary, a story written on its descent. City rain speaks of engines, chimneys, glass, and asphalt. Forest rain whispers of leaves, soil, and microbial breath. The molecules are identical, but their companions, sulfates or terpenes, soot or resin, change everything. To stand in either downpour is to read the sky above, to feel the difference between human-made air and nature's green chemistry. Rain has always been our familiar companion, falling since long before humanity drew its first breath. Yet the chemistry of raindrops is not fixed in time. It shifts with the atmosphere, echoing the gases, particulates, and energies that surround it. As the climate changes, so too does rain's composition. The drops that fall a century from now may bear signatures entirely different from those of today. Rain may feel eternal in rhythm, but in chemistry it is ever-changing. One of the clearest ways climate change reshapes rain is through acidity. Natural rainfall holds a pH of about 5.6, mildly acidic from carbon dioxide dissolving into carbonic acid. In the last century, industrial emissions of sulfur dioxide and nitrogen oxides intensified this acidity, producing acid rain that scarred forests, dissolved lakes, and eroded monuments. Regulations in many nations curbed these pollutants, and in some regions rainfall chemistry has slowly recovered, but warming temperatures and shifting winds now redistribute these pollutants in new ways, altering where acidity sharpens and where it softens. Places once neutral may see sharper rains. Places once acidic may experience relief. The map of rainfall chemistry is redrawn with every decade. Other forces add their marks. Wildfires, fueled by rising global heat, release immense clouds of soot, ash, and organic aerosols. These particles ascend, seed clouds, and fall within raindrops infused with carbon compounds and trace metals. Deserts, expanding under drought, release dust that turns rain alkaline, shifting its balance toward minerals rather than acids. In this way, climate change writes two signatures, fire and dust, into the story of each storm. Ozone, too, alters the tale. At ground level, tropospheric ozone rises in many regions, driven by heat, volatile organic compounds, and nitrogen oxides. Though not easily dissolved in water, ozone reacts with raindrops, contributing to the sharp scent of summer storms. As levels rise or fall, the fragrance of rain itself may subtly shift. That familiar tang after lightning, that cleansing sharpness, could change in ways our noses may notice before our instruments do. Even human experiments in weather leave their traces. Geoengineering proposals to seed the upper atmosphere with reflective aerosols would inevitably alter rainfall chemistry, embedding engineered particles in every drop. Cloud seeding with silver iodide already reshapes rains in some regions. If scaled up, rainfall would no longer be entirely natural. It would be water rewritten by human hands, each droplet a mixture of atmosphere and intention. This raises questions not only of science but of sensation. Will petrichor, the earthy perfume released when rain strikes dry soil, smell the same when microbial soils shift under changing climates? Will the ozonic tang of thunderstorms endure if the chemistry of lightning storms alters? Will future rains carry new scents, the signatures of altered air? Distribution, too, is changing. In wetter places, heavier downpours may wash torrents of pollutants into rivers, amplifying the role of rain as both nourisher and eroder. In drier regions, rarer rains may fall heavier, infused with the accumulated dust of long droughts, carrying a concentrated chemistry. Rainfall grows more extreme in both chemistry and frequency, mirroring the turbulence of the climate itself. And yet, there is hope. The story of acid rain has already shown us that the atmosphere responds quickly when emissions are curbed. Within decades, rain regained its softness in many regions. Cleaner energy, reduced fossil fuels, and wiser air management could allow tomorrow's raindrops to fall closer to their natural state. Clear, balanced, infused only with the faint traces of carbon dioxide, plant oils, and sea salts. What rain will always keep is its role as a bridge between sky and soil. Whether carrying soot, pollen, sulfates, or terpenes, each drop is a courier of its time. To study rain is to read the story of the air above, written in ions and molecules. The future may bring sharper acids, stronger alkalines, or new signatures of fire and dust. But rain itself will always fall. It will cleanse, it will nourish, it will return. There is comfort in that continuity. Evaporation, condensation, precipitation, the steps of the water cycle have turned without pause for billions of years, and they will continue long after we are gone. What shifts is not the rhythm which endures, but the content of each drop. What rides within the falling water is shaped partly by natural forces and partly by human hands. Each raindrop is a messenger, carrying with it the chemistry of its time. Perhaps that is the deepest truth about rain. Tomorrow's storms will be what we choose them to be. If we fill the skies with soot, raindrops will carry that soot back down upon us. If we clear the air, they will fall cleaner, lighter, gentler. If we alter the atmosphere with experiments or emissions, they will adjust in kind. Every drop is a mirror, falling steadily back into our grasp, reflecting our choices with quiet honesty. Rain is chemistry, yes, but it is also memory, reflection, and promise. Yet rain is something far more intimate than even chemistry can fully explain. It is rhythm against rooftops, the hush of drops threading through a forest canopy, the soft percussion of water on glass as night gathers outside. To physics, each raindrop is only a cluster of molecules, obeying the strict geometry of quantum mechanics. But to our ears and skin, rain is music. It feels like the sky is breathing, reaching down to touch us with a steady, tender pulse. Every drop is both order and randomness. On the molecular scale, water is precise, hydrogen bonds pulling molecules together, polarity shaping them into spheres, cohesion holding them in tension until they fall. Geometry dictates their curves, chemistry dictates their bonds, yet by the time they reach the ground, that perfect order has been scattered into playful chaos. Droplets splash and shatter, gather into rivulets, merge into puddles that reflect a shifting sky. Science explains the arc of their fall, but our senses transform it into lullaby, a song written in clouds, translated into rhythm as it touches earth. Rain connects us to time in ways few other things do. The water sliding now down a window pane is unimaginably old. It may once have been locked in a glacier, coursed through the veins of a dinosaur, or risen as steam from an ancient sea. Today it falls as a raindrop in our present moment. Tomorrow it will be vapor again, rising toward the sky, beginning its cycle anew. In each falling drop is both immediacy and eternity, freshness and deep antiquity. To hear rain is to hear echoes of ages long past, to witness molecules returning from journeys longer than history. Part of rain's comfort comes from its scent. Petrichor, the earthy fragrance after rainfall, is not merely a metaphor but a molecular message. Plant oils washed from leaves, microbial geosmin released from soils, and the sharp tang of ozone from lightning mingle in the air. These compounds trigger something deep within us, associations older than civilization itself. For our ancestors, rain meant survival, crops saved, rivers replenished. That memory lingers in us still. Chemistry becomes nostalgia, molecular interactions become calm, relief, even joy. Rain is also sculptor, shaping landscapes with patient persistence. Its mild acidity, born of dissolved carbon dioxide, slowly wears down stone, grain by grain. Rock dissolves, valleys deepen, caves grow wider. Over centuries and millennia, whole mountain ranges are softened by nothing more than raindrops falling, again and again. Each drop is gentle, but together they are architects of canyons, sculptors of cliffs, painters of landscapes, vast and subtle. When rain soaks into soil, its chemistry begins another quiet labor. It dissolves minerals, carries nutrients, redistributes the building blocks of life. Roots draw in what the drops deliver. Microbes stir to activity. Fungi extend filaments. Forests grow greener. Rain writes upon the land with the long handwriting of time, nourishing and reshaping at once. There is a duality to rain. It is both explanation and experience, science and song. Knowing that lightning fixes nitrogen into usable fertilizer does not make a thunderstorm less wondrous. It deepens the wonder. Knowing that a rainbow is refracted light within droplets does not diminish its beauty, but adds another layer of awe. To see rain scientifically is to marvel at its invisible structures. To feel rain poetically is to marvel at its rhythm, its scent, its voice. Together, they form a whole chemistry and meaning intertwined. Listen closely, and rain reveals itself as music. Each surface it touches becomes an instrument. Leaves whisper, roofs drum, windows patter softly, puddles echo with hollow plinks. The randomness of falling water organizes itself into rhythm, stochastic distributions becoming melody. Rain is a language of nature, spoken not in words but in notes and tones, in cadences that soothe the mind. Rain invites stillness. Its steady fall narrows the world, softens the edges of sound, and pulls our attention inward. Distant noises fade. Time seems to slow. In its repetition lies reassurance. This cycle has always turned, and it will continue. To sit with rain is to be reminded that continuity still exists, that something greater than ourselves carries on. Rain is chemistry, in service of calm, molecules, writing a score that nourishes earth and quiets the spirit at once. And rain is never neutral. In cities it reflects our presence, acidic, soot-laden, sometimes harsh. It eats away at stone, leaves films on glass, washes particles into rivers. In forests it carries fragrances of pine resin and soil oils, softer, nourishing, cleansing. These contrasts remind us that rain is always a biography of the air it passed through, a living record of the skies above. The poetry of rain lies in this interplay between fact and feeling. Hydrogen bonds, polarity, refractive indices, these explain the how. Rhythm, fragrance, calm, and memory explain the why. Rain nourishes crops and cleanses the atmosphere, but it also nourishes us inwardly, offering comfort, reflection, and renewal. In the end, perhaps rain is both teacher and companion. It teaches us about cycles, chemistry, resilience, and it accompanies us, offering solace in its rhythms. Raindrops fall indifferent to us, yet we cannot help but find meaning in them. Each drop is both molecule and music, both science and poem. To study it is to uncover hidden laws. To feel it is to touch the heartbeat of the planet. Every shower is a story. Every drop, a tiny archive. Rain is never only weather. It is cleanser, nourisher, sculptor, and storyteller. It rinses the dust from air and leaves. It feeds soils and rivers. It wears mountains into sand. It speaks of cities and forests, of exhaust and leaves, of past and future. It reminds us that even the simplest molecules can carry endless meaning. And as this reflection closes, one truth remains: rain will fall again tomorrow. It will fall the day after, and long after that, always the same cycle, always new chemistry, always science, always song. Rain will continue to carry with it the quiet chemistry of life, falling endlessly, patiently, whispering its stories into our waiting hands.